In this video, we're going to talk about section 4.1, which is actually differentials and linear approximation. Alright, so let's see. Differentials and linear approximation. So what is a differential? Well, we're going to let f be a function, let x and y be variables, so relate it so that y equals f of x, and then the differential dx, so that is just the differential, is a quantity that can take on or be assigned any value in R. And this R is actually referring to the real numbers, or actually you might know it as negative infinity to infinity. Alright, so if x is any number in the domain of f for which the first derivative, f prime of x, exists, then the differential dy is defined by dy equals f prime of x dx. So we're going to find the differential dy of each of the given functions. So here we know that dy is equal to f prime of x dx. So we need to find the derivative of this function right here. Alright, so dy is actually 2/3 x to the minus 1/3 dx. So that is the differential. So that was easy enough to find. Alright, so let's actually scroll down a little bit, and well, I don't know why I can't just scroll down to the next one here. Okay, so let's do problem number 2, part B now. So I'll clear the screen here so that we can do part B. So now, remember that dy, what we're trying to find, is actually f prime of x dx. So dy is equal to, and what is the derivative here? Well, this is actually 9 minus x squared to the 1/2. So this is actually going to be 1/2. 9 minus x squared to the minus 1/2. And then we need to use the chain rule. So we multiply by the derivative of 9 minus x squared, which is negative 2x. And then we have dx over here. Alright, so now we know that 2 cancels with this 2. So dy is actually equal to, now we have negative x over here, so we have negative x times 9 minus x squared to the minus 1/2 dx. So this is actually going to end up being a dy equals negative x over 9 minus x squared to the positive 1/2 dx, or actually dy is equal to negative x over the square root of 9 minus x squared dx. Alright, so now let's try problem C here. So we know again dy is equal to f prime of x dx. And I'm going to rewrite this as x to 1/2 plus x to minus 1/2 to make it a little bit easier to find the derivative. So dy is equal to 1/2 x to the minus 1/2, and then minus 1/2 x to the minus 3/2, and then dx. And then if I rewrite that without the negative exponents, it's 1 over 2x to the 1/2 minus 1 over 2x to the 3/2, and then dx. Or you could even simplify a little bit, and it could be dy is 1 over 2 square root of x minus 1 over 2, and then the square root of x to the 3rd dx. So that's another way you can rewrite it. I mean, you could be simplifying that all day and rationalizing the denominator. That's fine. So we're almost out of time in this video, so I'll pick up with example D in the next video. In this video, we're going to finish page 137. So let's do example D here. So remember, we're just trying to find the differential dy. So dy is f prime of x dx. So we're going to need to use the product rule to find this derivative. So let's say that u is e to minus 0.5x, and then v is cosine of 4x. And then we need to find du dx and dv dx. So du dx is going to be negative 0.5 e to minus 0.5x. And then dv dx is going to be minus 4 sine of 4x. So we know that dy then is going to be, and remember the product rule is u dv dx and then plus the du dx, so then times dx. So actually this is dy is actually, let's see, e to minus 0.5x times dv dx, which was the minus 4 sine of x times sine of 4x. So let's see, let me write 4x so that's a little bit more clear what's going on here. So I don't know why my pen did that, but sine of 4x, and then plus we have a v, so cosine of 4x, and then a du dx negative 0.5 e to minus 0.5x, and then we have the x at the end. So you could simplify that a little bit if you want. I mean, there's not much that you could do. You could rewrite it as negative 4 e to minus 0.5x sine of 4x, because I know that some of you like putting that constant, the negative 4 in front, and then minus 0.5, and then e to minus 0.5x cosine of 4x. I know some of you out there in this class would want to try to factor something out. I mean, you can factor out the whatever you want, but you're actually done here. I won't ask you to simplify anything more than that. So that is the end of page 137, and I will see you in the next video. In this video, we're going to start page 138. So let x and y be differentiable functions of a third variable t. So differential functions of a third variable t, and suppose that y to the fourth plus 2x squared y squared plus 6x squared is equal to 7. And then we're going to find the relationship between dx and dy. Alright, so that means that we're going to need to use implicit differentiation. Alright, so if we find the derivative of this y to the fourth, that's 4y to the third dy dx. Now we need to find the derivative of this 2x squared y squared, and we need to use the product rule. So u is going to be 2x squared and v is going to be y squared. So du dx is actually going to be 4x. Alright, and then dv dx is going to be actually 2y dy dx. Alright, so by the way, what this is actually going to do here is something actually a little bit different than what you're probably used to. We're actually going to write that 4x is 4x dx over dx. Alright, and if you notice, that's still 1. Dx over dx is 1, so that's still 4x. Alright, so we have, using the product rule here, this is going to be the 4xy squared dx over dx, and then plus the 2x squared times the 2y dy dx, and then we're going to find this derivative right here the same way as the derivative of the 2x squared, so it's going to be 12x, and then a dx over dx, and then the derivative of the 7 is equal to 0. Alright, so we're actually going to multiply by dx, multiply through by dx. So let me actually erase this product rule part now, since we're done with the product rule over here. So that's sort of out of the way. Alright, so now we're going to multiply by this dx here, so that this dx cancels, this dx cancels, this dx cancels, this dx cancels. Alright, so now what we have is actually 4y cubed dy plus 4xy squared dx plus 2x squared times 2y dy plus 12x dx is equal to 0. And then here is a term with dy, and here is a term with dy, and I'm actually going to write that as 4x squared y, so that it makes this part a little bit easier to understand. So I'm going to combine the parts with the dy's right here in front. So 4y squared dy plus 4x squared y dy, and then the parts with the dx is right here and right here, so a plus 4xy squared dx plus 12x dx equals 0. And this is how we've solved for the derivative in the past. We're just going to factor out a dy right here. So we have 4y cubed plus 4x squared y dy, and then we have dx's right here. So we have plus 4xy squared plus 12x, and then times dx is equal to 0. So there is a relationship between dy and dx. So I know that was a little bit of a complicated problem because of all this implicit differentiation, but we'll pick up with the rest of this page in the next video. In this video, we're going to finish page 138. So here we have the linear approximation theorem. So if the function f is differentiable at the number x1, then for all values of delta x for which x1 plus delta x is in the domain of f, then f of x1 plus delta x is equal to f of x1 plus f prime of x1 delta x plus delta x times this epsilon. Now, this is where the quantity epsilon satisfies the condition that the limit as delta x approaches 0, epsilon is equal to 0. So you can think of this epsilon as an error. So I hope that you would agree that you want this epsilon, this error, to be 0. And that's why you want this limit as delta x approaches 0 epsilon to be 0. Now this part right here, this f prime of x1 delta x, that is actually delta y, and so delta y is actually going to be f of x1 plus delta x minus f of x1. Alright, so now let's do an example of all of this. If y is equal to 1/2 x cubed, compare delta y and dy if x equals 2 and delta x is equal to dx, which is equal to 0.1. So let's find dy. Now remember, the formula for dy is f prime of x dx. So that is telling us that we are using calculus here. Alright, so we're using calculus to find dy. Alright, so dy is going to be the derivative of 1/2 x to the third is 3/2 x squared times dx, and then dy is going to be, now remember that x was 2 and then dx was 0.1, so this is going to be 3/2 times 2 to the second times 0.1, and that means that dy is 0.6. Alright, now, if we want to find delta y, this is done without calculus. So we're going to see if this linear approximation is actually close or not. This approximation without using calculus here. So, this is f of x1 plus delta x minus f of x1, what I just told you up here. Alright, so this is f of 2 plus 0.1, because that's what x and delta x were, and then minus f of 2 because that's what x1 was, so this is f of 2.1 minus f of 2. So this f is the original function, remember, so that was 1/2 x to the third. So this is 1/2 times 2.1 to the third minus 1/2 times 2 to the third. And this is actually, using your calculator, 0.6305. And that is what we call a linear approximation. So in this case, I hope that you can agree that this linear approximation of 0.6305 was actually really close to this differential of 0.6. Alright, so we'll do another example in the next video. In this video, we're going to finish up page 138. So we're going to use differentials to approximate the following. So in this problem A, it's the square root of 99.4 that we're going to approximate here. So we need an f of x. So f of x, how about we just use square root of x, because we're trying to find the square root here. Now remember that we need to actually find the derivative here. Okay? So the derivative, f prime of x, is actually going to be, if this is x to the half, 1/2 x to the minus a half, or 1 over 2 square root of x. Alright, so if we're going to use differentials to approximate the following, remember that the f of x plus delta x is approximately f of x plus f prime of x delta x. Alright, so we're going to actually need to substitute a number into f of x that we can find the value of easily. And a number that's really close to 99.4 that we can find the square root of easily would be 100. So I'm going to let x be 100. And then delta x is going to be the difference between that x and the number we're actually trying to find. So this is actually going to be negative 0.6, because 99.4 is 0.6 less than 100. That's why it's negative. And so x plus delta x here is 100 plus a negative 0.6, which is the 99.4 that we're actually trying to find right here. Alright, so that means that f of 100 plus negative 0.6, or f of 99.4, which is what we're trying to find, is approximately f of 100 plus f prime of 100 times delta x, which is negative 0.6. Alright, so f of 100 is actually the square root of 100, and then f prime of 100 is 1 over the 2 square root of 100 times the negative 0.6. And then this square root of 100 is 10, and this square root of 100 is 10, and then we have negative 0.6. And so this is actually 10 minus 0.03. Now theoretically, the reason why we do this is so that we can try to approximate this square root of 99.4 mentally, but with that being said, you could still use a calculator right here, and then this is actually 9.97. So that is our approximation. Alright, now if you want to know how close that is, the actual value of the square root of 99.4 is about 9.96995. So I hope that you agree that our approximation of 9.97 was actually really close to the actual value. So that is the end of page 138, and we'll do another example in the next video. In this video, we're actually going to start on page 139. So we're actually going to use differentials to approximate 2.99 to the third. So this is actually the same procedure as in the last problem. We're going to find f of x plus delta x, which is approximately f of x plus f prime of x times delta x. So we need a f of x. And this looks like we're just cubing a number. So I'm going to make that x cubed. And then we need the derivative. So that derivative is 3x squared. And then an x that is close to 2.99 that's easy to cube would be 3. And so delta x is actually then negative 0.01, since x plus delta x has to equal the 2.99, so 3 plus a negative 0.01 is 2.99. Alright, so this is the same procedure. f of 2.99 is approximately f of 3 plus f prime of 3 times the delta x, which is negative 0.01. So f of 3 is 3 to the third, and then f prime of 3 is 3 times 3 squared times negative 0.01. So again, this should be able to be done mentally. So 27 minus 0.27, which is 26.73. But you can use a calculator if you want. Again, this is still, if you're thinking out how you would do this mentally, easier than doing this mentally, right? Alright, so this is just the approximation, but the actual value of 2.99 to the third, and let me make that third a little bit lower for you. 2.99 to the third is actually 26.7309. So I hope you agree that this is actually a very good approximation of 26.73. Alright, so I have good news for you. We have time for an application problem in this video. So let's do A. The measurement of a side of a square is found to be 12 inches. And that has a possible area, or a possible error of 1/64 of an inch. So we're going to use differentials to approximate the possible propagated error in computing the area of the square. Alright. So we know that a square, my pen went away. We know that a square has equal sides, so x, 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 x. Alright, so we want to compute the area. So the area of a square is actually going to, in this case, be x squared. So if we find the differential, that's going to be dA, for area of course, is 2x dx. This is the propagated error that they're asking us to find. Okay, so I'm not sure I spelled propagator right, but let me make sure that I have propagated error that they're trying to have us find here. Okay, so we know that x is actually 12 inches. So x is 12 inches, and we know that the error, delta x, or in this case just dx, is plus or minus 1/64 of an inch. So let's substitute this in to just find the propagated error in computing the area of the square. So it's 2 times 12 times plus or minus 1/64. And so this actually ends up being plus or minus 3/8 inches squared. And so that is the propagated error for the computed area of the square. Alright, so we're out of time for this video. We'll do the next example B in the next video. Alright? Alright, I have great news. We're going to finish page 139 with another application problem. So the measurements of the base and altitude of a triangle are found to be 36 and 60 centimeters respectively. So I'm just going to draw the triangle here. So the base is going to be 36 centimeters, and the altitude or the height here, the altitude or the height is going to be 60 centimeters. The possible error in each measurement is 0.25 centimeters. Use differentials to approximate the possible propagated error in computing the area of the triangle. So the area of a triangle, if you remember, is a half base times height. So the propagated area, dA, is a half, and then B times 1, and then dH, and then a plus a half times 1 times H times dB, because remember, we need to use the product rule in computing this particular derivative. Alright, so we know B is 36, A is 60, and we know dH is equal to dB. dH is equal to dB, and those were both equal to 0.25 centimeters. Okay, so just plug everything in here now. So this is a half times 36 times 1 times 0.25 and I'm not even going to write that 1 because I don't think I'm going to have enough room. So I hope you don't mind that I just, know that that 1 is still there. And then plus a half times 1 times h, which was actually the altitude. Remember, it's altitude, right? Altitude or height, right? It doesn't really matter what we call it, A or H. So this is actually 60 times dB, which is 0.25. And so now this is going to be 18 times 0.25, and then plus 30 times 0.25, and that is going to be what? So this is just going to be 12. Now remember that this measurement could be over by 0.25 or under by 0.25. So we actually say this is actually plus or minus 12 centimeters squared. So this is the propagated error for computing the area of the triangle. Alright, so that is the end of the section. I'll do a couple of extra examples in the next couple of videos. Alright, so I'm going to do an extra example right now just so that you'll have an extra example, okay? So this example is just use differentials to approximate the function at the given value of a. So let's say you are given f of x is equal to 5x squared plus 5x plus 5, and then a is equal to negative 3. Alright, so when I say you're going to approximate this, I'm talking about L of x. This is what I call linear approximation, alright? This is f of a plus f prime of a times x minus a. So this means that we're going to need to find f prime of x, and this is not that hard to do. In this case, it's just 10x plus 5, alright? So we need f of negative 3, because a was negative 3, plus f prime of negative 3 times x minus negative 3. Alright, so f of negative 3 is actually 5 times negative 3 squared plus 5 times negative 3 plus 5, and then f prime of negative 3 is actually 10 times negative 3 plus 5, and then we have times x plus 3 here. So let's just simplify this. This ends up being 35 plus a negative 25 times x plus 3, or 35 minus 25x minus 75. And so if we simplify that, we have L of x, the linear approximation, is going to be negative 40 minus 25x. So that's just another extra example that I think may help you in the future. So we'll do a couple more extra examples in the next video. Alright, so in this video I'm going to do another extra example, so number 2. I want to just review finding the relationship between dx and dy, since I know that implicit differentiation can be a little bit confusing. So let's say I have x squared plus xy plus 3y squared is 51. Alright, so if we just go with differentials here, then this is going to be 2x dx. You don't have to do that dx over dx business if you don't want, but you can. And then this, you have to use the product rule, so xy, and we have u is actually, let's see, x, and v is y, so du dx is actually dx over dx, right, or 1, and dv dx is actually a 1, and then dy dx, so this is actually going to be plus x dy dx, and then plus y dx over dx, and then plus 6y dy dx, and then the derivative of 51, which is 0, and then you multiply by that dx to clear all of the dx's out. So you're left with 2x dx plus x dy plus y dx plus 6y dy is equal to 0. Group the terms with the dx's together, so 2x dx plus y dx, and then the term with the dy's together, plus x dy plus 6y dy equals 0. Then factor out the dx's, so 2x plus y dx, and then factor out the dy's, so we have plus x plus 6y dy is all equal to 0. And that is the end of this extra example. I hope that you enjoyed that. In this video, let's do another example, and this will be example 3 of using differentials to approximate a value. So here I'm going to approximate 1 over the 5th root of 31. Alright, so I need to make a function that's close to this, so 1 over the 5th root of x seems like it would be a good idea, and that's x to the negative 1/5. And now I need the derivative, the first derivative, f prime of x, that's negative 1/5 x to the minus 6/5, or negative 1 over 5 x to the 6/5. Now I need to substitute a number into this function that would be easy to take the 5th root of, but that is close to 31. So how about 32? Because the 5th root of 32 is actually 2, alright? So that's an easy one. And then we need delta x, which is negative 1, because 32 is minus 1 is 31, alright? So x plus delta x is 32 plus a negative 1, which is 31. So this is the same way as before. We have f of x plus delta x is approximately f of x plus f prime of x times delta x. So this is equal to 1 over the 5th root of actually 32 plus a negative 1 over 5 times 32 to the 6/5 times the delta x, which is negative 1. Alright, so if it wasn't clear, let's just say that was f of 31 is approximately, right, f of 32 plus f prime of 32 times the negative 1. Alright, so now we know the 5th root of 32 is 2, and then we have minus 1 over 5 times this is actually the 5th root of 32 to the 6th power, alright, times negative 1. And so this is a half minus 1 over 5 times 2 to the 6 times negative 1, or a half minus, let's see, let's just multiply that times the negative 1 and make that plus. And then we have 5 times 2 to the 6, which is 320. So if we find a common denominator, that is going to be 160 over 320 plus 1 out of 320, which is 161 out of 320. And again, the whole goal of this is that you could potentially do this division by hand more easily than this original problem, alright? But you can use a calculator if you want here, and this is approximately 0.503125, and the actual value of 1 over the 5th root of 31 is 0.503184,971. So our approximation was actually very close. So that is the end of the extra example, and we'll see you in the next video.